It's great to be here. So thanks for inviting me and including our paper in this wonderful conference. So thanks for joining our talk here in person and also those who join online. So this is joint work with my colleague, Wenxi, Gavin. So he actually should be here soon, and Chao Zhang at University of Oxford. I am trying to use the clicker, but it doesn't seem to be on. It's probably off or yeah, I'll just use the keyboard. Now, there are lots of characteristics, as we see in the morning, the keynote speech by Stefan Nagel, lots of characteristics that can predict stock returns. So by some count, there are over 400, and Cochrane in 2011 called it a factor zoo. So machine learning has an advantage of using lots of characteristics to predict returns because they are designed to handle a lot of independent variables. And also they can select among all these noisy and correlated predictors and allow nonlinearity and complex interactions among the predictors. Now, however, there is an important concern that is overfitting, right? So although there are some regularization techniques to address the concern, it is still something that we all need to think about, right? Because there are thousands of parameters and some hyperparameters which are chosen by the researchers. So these hyperparameters are to define how the model structure look like. The results can be sensitive to the choice of these hyperparameters. Now, Caroli and Van Nieuwburg, in a special issue of RFS, in fact, they also noted this concern and said, most of the existing studies only use one market. The only out of sample, so you classify the sample period, some of it as out of sample, but most of them come from the US. So in this paper, we do something very simple. We just use other people's methodology to predict stock returns in 31 international markets. Okay, so this is very simple. And particularly, we follow one paper by Gu, Kelly, and Xiu very closely, GKX, in 2020. They examined the US market using 94 characteristics, 8 macroeconomic variables, and 74 sector dummies, and plus some interactions. So the total number of predictors they have is over 900. So we use their methods and use their set of potential hyperparameter values and to predict international stock returns. Now, however, we cannot follow their list of predictors exactly because the data availability is lower internationally. So we only use 36 characteristics. So we didn't choose the 36. We just use the 36 that we can download a reasonable long time period in order for us to conduct our studies. Now, today I won't have time to show you. If we just look at the US, our US results are similar to those in GKX. Now, this is not too surprising. In fact, GKX's own paper shows that if you use 20 to 30 characteristics, you also get very strong results. So you don't really need the 900. Okay, so some other studies also show like if you use a 10 to 30 characteristics to predict in a machine learning context, you can predict the cross-section of the US stock returns quite well. Okay, so following GKX, we compare different classes of models. We have linear models, OLS and the variance, OLS with Hooper laws, Lazo, Rich, and ENet. We have the tree models, the random forest and the GBRT, the gradient boosting regression trees, and the neural network models, the NN models with 1 to 5 hidden layers. Now we have 3 major findings here. The first one is we conduct a very stringent out of sample test. We train and validate our models using US data. Okay, so we have the US data, we train our model in the US, but apply the US estimated parameters and hyperparameters in the international market. Okay, so in the statistical sense, this is a out of sample test. So we train something in the US, apply them out of the US. So in this test, the machine learning models do quite well. NNs, the neural networks, and the trees outperform linear models in terms of forming profitable portfolios and predicting stock rankings. the return rankings. However, not so much on the R squared. Okay, so we'll talk more about this later. In fact, a recent paper by Kelly and co-authors also make a theoretical argument that R squared might not be a good measure of the economic value of the models. Okay, so we find something similar, probably because of the extreme values of international stock returns. Okay, so the conclusion here is they work quite well. Now, then we do something different. We try to use our test to answer some questions in the international finance literature. So one question they want to know is whether stocks are priced locally or globally. Now, the second test we do is, instead of just using the US data to train the model, now we train each model in each market. We train our models separately for each market. Okay, so note that there is a drop of number of observations here, right? Because as I will show you later, the US has the most number of observations, but then if you use the international data, the number of observations drops substantially. Okay, so this is also a test to put the machine learning models to test, right? So like under a fewer number of observations and with a different data structure, do they still work? Okay, so and the advantage here is machine learning allows us to develop local models without even knowing the institutional details in each market, right? So typically, if you want to develop a model for China, you need to know some institutional details, right? So you need to know what variables to include because the Chinese investors are different from the US investors, etc. Our method using the machine will pick up the variables that are important. We just feed into the machine, and then the machine will develop these local specific models. Now in this test, NN, the neural network, continues to perform very well. So they each actually produce even stronger results. But 3 models in this test actually underperform linear models, especially in markets where the number of observations is low. Okay, so it seems that the trees' performance are sensitive to the number of observations used. Now, to answer our questions, should stocks be priced locally or globally? Our evidence suggests that local NN models dominate a global NN models trained by the US data. And we also see bigger improvements in the profitability when the local NN is less similar to the US trained NN. Okay, so here we don't even need to look at the economic details of each market, right? Because the machine learning technique tell us how similar or dissimilar the 2 markets are, right? So there is a standard index, the CKA index, to tell us the markets are not similar, then the improvements of the local NN over the global NN is even larger. And also this happens when the NN, the neural network, has more hidden layers. So these are consistent with the fact that you need some deep learning to incorporate the local specific features to help you further improve the return predictability. Now, the last thing we look at cross-market integration. Now, although local NN models work well, we can still add some international variables. Okay, so this is still challenging using traditional parametric methods because you need to specify which variables to add and how to interact the international variables with the local variables. So the idea, the advantage here with machine learning is we feed these into the machine and the machine will pick. Okay, so here we follow the literature that uses the US to predict international returns, right? Because US is the largest stock market, is the largest trading partner for many countries, it's relevant for a lot of markets. So here we add US-based variables to the local NNs. So we find that the US characteristic gaps, so defined as the value of the characteristic, the 95th percentile minus the 5th percentile. Okay, so this is not the return. This is the value of the characteristic, 95th percentile minus the 5th percentile, and interact with the local characteristic that can improve further our local NNs. Okay, so in a word, the local NNs work well, better than the global version, but it is the local with the US-based variables that work the best. Okay, so if you want to interpret market integration, you can say that the market is not fully integrated in the sense that a global market will work, a global model will work, but you need some international factor. So meaning that the market is partially integrated. Okay, so it's the local plus the US variables that work the best. Now our data, 36 variables, you can refer to the paper for the list, but it includes the most common characteristics, the most accessible, easy to download, past returns, market cap, volume, past returns of the industry, accounting information, we just download from DataStream. Now for the US data, we use Cribs because the availability is better. For China, we use Sysma. We require at least 100 stocks for at least 3 years for all the 36 characteristics. So that leaves us with the 31 international markets plus the US. So follow GKX. We divide the sample periods into 3 parts. We have the training period, where we estimate the model subject to a particular set of hyperparameter values. And then we have the validation period, where we construct the forecast, the returns forecast, and calculate the objective functions based on the parameters estimated from the training period. But for each set of hyperparameter, we repeat this, where we repeat until we search for the best set of hyperparameters that optimize the objective functions. Okay, so and then we have the testing period, which is not used for estimation or for the tuning of the hyperparameters. These are the out of sample testing period, as in the standard literature. And also standard is we standardize the predictors on the right-hand side in each month in each market to 0 mean and unit standard deviation. Our outcome variable is the excess return in US dollar in the next month. And here is defined in USD and in excess of the corresponding market return. Okay, so this is not in excess of the risk-free rate. We focus on the cross-section of the stock return here, so we subtract off the market return. Although in an earlier draft of the paper, we did that with the US risk-free rate, the results are very similar. Now in the model, we will report the following. We have an annualized Sharpe ratio. This is the Sharpe ratio of a long-short portfolio, where we long the top decile of the predicted returns. Our model generates predicted returns. We long the top decile and short the bottom decile and look at the realized Sharpe ratio, annualized Sharpe ratio. And then we have the out of sample R squared coming from the testing period. Although later I will argue that out of sample R squared again is not the best measure. We have a rank correlation measure, which is less affected by the outliers. We use the rank correlation between the predicted returns and the realized returns. We also look at a decile score distance. So this is focusing on our long short portfolio, right? So remember we long the top decile of the predicted returns, but we also look at the actual return deciles of that long portfolio. And then we short the lowest decile of the predicted returns. We also look at the actual return deciles of that short portfolio, right? So if our model is predicting everything perfectly, the long portfolio would be in the actual return decile 10, and the short portfolio would be in the actual return decile 1, then this distance is line. Okay, so on the other hand, if our model has 0 prediction power, then the actual deciles will be on average 5.5. Okay, so and then the distance will be 0, is 5.5 minus 5.5. Okay, so the larger the better. That means we can sort the top deciles and the bottom deciles really well. Okay, so and then the last thing is we can also use some standard methodology, the sum of the squares of the partial derivatives, to measure the variable importance. Okay, so I have given you the main message of the paper. The rest of the talk is just a lot of numbers. Okay, so I will show you lots of evidence. Now here first, I want to show you the 32 markets, so 31 plus the US. Now this is sorted by the number of observations. So we have 2 pages. So this is the first page, and then the next page has another 16 markets. So here at the top is the US. US has like 2.4 million observations. So this is the last row there. Sorry, the last column there. Now followed by Japan, China, India, but note again, the number of observations drop a lot, right? Because the sample in the US, it started in 1963, but in Japan, for example, it only started in 2008, right? Because we need to get the characteristics. Now, and remember at the beginning, I said, we separate the sample period into training, validation, and testing according to the proportion that the GKX paper uses. So we've just followed their methodology. Okay, so this is the bottom half. So like all the major markets are covered. Now I show you the first result on the US trained models. So again, this exercise is to use the US data to train and validate the parameters and the hyperparameters, fix these, and predict each of the 31 markets, international markets. Okay, so a very stringent test. Now, again, these countries, so each row is a country, they are all sorted on the number of observations. So this page is the top half, and then the next page is the bottom half. So what we report here, the numbers are the equal weighted Sharpe ratio. The Sharpe ratio when we long the top decile and short the bottom decile. In each row, we report the different models, the OLS3, which is the OLS model with the 3 Farmer-French characteristic. And then the OLS model, lasso, ridge, random forest, the GBLT plus H, which is the gradient boosted regression trees. And then the remaining 5 columns are the NN1 to NN5. In each row, in each market, we highlight the highest number. Okay, so in this, if you look at where do you see the colors, they are mostly on the right-hand side of the slide. Okay, so meaning the machine learning models, the NN models in particular, they get the highest Sharpe ratio in this exercise. Okay, so you see these numbers are generally larger than 1.5. Many of them are larger than 2 or even higher. As these are the equal weighted Sharpe ratio. This agrees with the GKX exercise focusing on the US. Okay, so this is the bottom half of the countries. Quite similar pattern, right? So the right-hand side, you have more colors, right? So these have the highest Sharpe ratio in each of these markets. Now we repeat this. So this is still the US trained model. We repeat this with the value weighted Sharpe ratio. Okay, so just similar exercise, but instead of equal weighted, we do value weighted. But similar message, right? So the machine learning models, especially the NN, usually gives the highest value weighted Sharpe ratio in each market. Now these numbers, if you look at the magnitude, they are smaller. That's not surprising because the value weighted Sharpe ratio weights more the larger stocks, and then the predictability there is smaller. It's more difficult to predict the large stock return. And then these numbers are generally around 1 or around 1.5. Okay, so smaller than before, but still NN models are powerful. Okay, so in the bottom half, slightly weaker pattern. You see some highlights go to the left with the lin on the right-hand side, and in particular in the NN models, the last 5 columns. Okay, so I show you the same picture for the R squared. Top half of the countries, bottom half of the countries. So you see, R squared does not show the same pattern, right? So R squared is a bit more all over the place. And sometimes the OLS3 model actually dominates. Okay, so this is particularly in the bottom half of the countries. And in fact, if you look at the column of the random forest and the GBRT, you sometimes see very negative R squared. Okay, so meaning that these 3 models actually don't do well in terms of R squared. Okay, so but we follow the theoretical argument by Kelly and co-authors and some other papers, and think that particularly in international returns, there might be extreme values. So these R squared might be affected by the extreme values, right? So that they may not, so machine learning models do not do well here. Okay, so because the predicted values and the actual values, they can be both very extreme. Now, we look at some other measures. So the rank correlation, which is not as heavily affected by the extreme values because we are looking at the rank. Again, this is the rank correlation between the predicted returns and the actual returns. Okay, so again, for each market, we compute these. So these are in percentages. They are like slightly less than 10%. Okay, so and you see now the 3 models are doing well. Okay, so 3 models sometimes have the highest value in these markets. Okay, so but generally, you see the pattern, the machine learning, the complex models, the 3 and the NN do better than the OLS, the variance and the lasso and the ridge. Okay, so like you see more highlighted values on the right-hand side. So similar for the decile score distance. So decile score distance focus on the long decile and the short decile that we predict the top and the bottom deciles of the return. And then again, we highlight the highest value. Most of them are on the right-hand side. Okay, I show you a lot of numbers here. And this is still the US trained model. Here is a summary. Okay, so and then after this, I will move on to the country-specific model. Okay, so but for the US train model, so a summary here is if we look at the Sharpe ratio equal weighted, so this is the average distance between the best tree model and the best linear model. Okay, so for each class of models, we select the best, and then for each country, we compute the difference. This is the average across all the 31 markets. Tree minus linear is 0.41. Okay, so 0.41 here. And we also look at the number of positive values, right? So out of the 31 markets, 26 of them is positive. Okay, so that means the best tree outperformed the best linear model in 84% of the markets. Okay, so 26 of 20 out of 31, that's 84%. Okay, so we see generally, except for R squared, trees and NN, they outperform linear, in particular NN. Okay, so NM performs the best, tree follows, and then linear. Okay, so this is the message we get from the US trained models. Okay, so with the exception of the R squared. Okay, so but again, we think R squared not the best measures, probably because of the extreme values. Now, let's move on to the country-specific models. Okay, so here, remember, we don't force the parameters and hyperparameters to be the same from the US model. So here we train all the models separately for each country. Japan is allowed to have the Japanese models. China is allowed to have the Chinese model, all trained from the own market's data. But remember, the number of observations would drop a lot, right? Because in the previous test, you can still use the long history of US data to train your machine learning model. So here we need to rely on each country's shorter sample period. Okay, so here is the summary. So instead of showing all the individual tables, I only show you the summary. Okay, so similar as before. So this is the average distance between the best tree, best linear, and the best NN. Okay, so here, if you look at NN minus linear, or NN minus tree, they are mostly positive. Okay, so like the difference is positive, and the number of positive values is usually 70% to 80%. Okay, so NN outperform linear models in 70% to 80% of the markets. Same thing for tree. NN outperform tree in 70% to 80% of the market. NNs continue to outperform. Now, one thing that is different from before is trees actually do not seem to outperform so well. Okay, so if you look at these measures, tree outperform linear in 59 of the markets in terms of the Sharpe ratio. In terms of the value weighted Sharpe ratio, only 38%. Decile score distance, rank correlation, slightly more than half. Okay, so and the average value sometimes is negative. Okay, so trees show signs of overfitting. They don't quite perform well, even compared with the simple linear models, especially in markets where the number of observations is low. Okay, so now to prove the last point, we put things into a graph. So here is the tree minus the linear on the left, and the NN minus the linear in terms of the Sharpe ratio equal weighted. We plot that as a function of the log number of observations, and we try to fit a line. So the left-hand side, you see upward sloping line, and even for NN, you also see an upward sloping line. So generally, the machine learning models, both tree and NN, they work better for more number of observations. But when you look at the level of these two lines, the left-hand side, tree minus linear, is sometimes in the negative region. So the red line is a 0. So many of these are in the negative region, so meaning tree actually underperform the linear. But the NN minus linear, they're usually in the positive region. Okay, so they're both sloping upward, but the tree minus linear is a lot of times in the negative region. Okay, so actually even stronger for the other measures. The Sharpe ratio ratio value weighted in the bottom, and then the rank correlation on this slide, and also the decile score distance. Okay, so again, we claim that NN still perform quite well here, very well here, but trees may not be, especially in the bottom half. Now, again, to answer the international finance question, should stocks be priced globally or locally? Then we can look at our country-specific models versus the US trained models. Now note that we cannot just compare the numbers directly in the tables because they are of different sample periods. The US models have longer sample period. So here, in order to make a fair comparison, we have to restrict the two classes of models to have the same sample periods. Okay, so and here we do that and then report the difference. So this is just the average difference across the 31 markets. So Japan, we have the Japan model minus the US trained Japan model. Okay, so and then look at the difference. They are mostly positive. Country-specific models dominate a global model that is trained by the US data. Okay, so meaning that we really need to take into account the market-specific details. But again, the machine doesn't know. The machine doesn't know China is dominated by retail investors. China does not allow short selling for a long time. Machine doesn't know. But the machine still predicts the Chinese specific market, the Chinese specific model does better than a US trained model that applies on Chinese data. Okay, so and then we also see bigger improvement when the two markets are more different, okay, so or less similar, right? So measured by this CKA similarity in the last hidden layer of the NN model. Okay, so we see again these numbers are mostly positive, all positive here, but they are bigger in the top row, the low CKA similarity versus the bottom row, especially for the deeper hidden layer, for the with more hidden layers, the more sophisticated models like NN5, NN4. Okay, so low CKA similarities and more hidden layers are associated with larger improvements, consistent with the claim that you really need to know the machine needs to know the market-specific detail and then use the deep learning to use them in the market-specific model. Now, in the last test, we do a global NN model, pulling all stocks together with 31 country dummies that generates an equal weighted Sharpe ratio of 3.9 and value weighted Sharpe ratio of 1.69. Then to this model, we add some US stuff. But this is a global model predicting global returns. We add some US variables. US factors form similarly as usual as some factors based on the top decile return minus the bottom decile return. The characteristic gaps, the value of the characteristics, not the return, but the 95th percentile value minus the 5th percentile value, and some local factors to this global model. Now, in terms of the number of variables, there will be a lot because there are 36 characteristics. The US-based variables and the local factors, minus the original global model. Okay, so then we see some improvement, again, in the Sharpe ratio, the equal weighted, and the value weighted Sharpe ratio. Okay, so meaning that local models with US details are even better. Okay, so we also see the variable importance. The orange line is the US characteristic gap. In many years, they are as important as the local stock characteristics, right? So in contrast, the US factors and the local factors, they are not as important. Okay, so in the last test, we focused on the US characteristic gap and then do that to the local, the market-specific NN model. For each model, we add the top 10 US characteristic gap and also interact them with the respective characteristic and then look at the Sharpe ratio, equal weighted, and the value weight. Okay, so generally you see improvements here, especially for the value weighted Sharpe ratio in the bottom and for the deeper layer model for like NN4 and NN5. Again, not surprising because you will need the deep structure to learn about the US interaction. How does the US bring to the local specific model? And the last result, why the value weighted Sharpe ratios have bigger improvement, probably because larger stocks in the local market, they are more related to the global market, to the US market. Okay, so they benefit more by adding the US characteristic there. Now to conclude, we do something very simple. We use something that has been done in the US, the machine learning techniques, apply them internationally. We have high Sharpe ratios. We did two things. We train and validate the models using US data or separately for each market. NN models pass both tests. They are powerful in both tests, and suggesting nonlinearity and complex interactions are important. Tree models do well when there are more number of observations in the US trained models in particular. In the market specific models, they suffer because the number of observations drop a lot. Now, country specific models generally dominate US trained models. So market specific details are important, but the markets are not totally segmented, right? Because the local NNs can be further improved by adding US-based variables, right? So meaning that the markets are still partially integrated, but not fully integrated in the sense that we only need one global model. Okay, so that's all, and thank you.
So I'm the chairperson for the afternoon section and also the first discussant in afternoon. Find my slide. So it is my pleasure to discuss the paper. So first of all, this paper applies machine learning for stock return prediction to the international stock market. When people talk about machine learning for the academic finance paper, then they will think about high dimensional problems to avoid model overfitting, or they might think about nonlinear models, the relative performance over those linear counterparts, okay? But this paper, the authors find a very good way to demonstrate the advantage for machine learning methods, that is they try to tell what I see that's like a hierarchical story, okay? They try to see whether stock returns are priced or predictable locally or globally. So the market specific models, what they find that is generally outperform, they are US trained models. So those characteristics can be used for US data, or those models can be used for US data. And then first of all, they find they're also useful for international stock market. And then they find once they use the international stock market data to train the model, then they get better results for that. Okay, so we might see some hierarchical structure to across those like international market from France to Hong Kong to Germany. So we see this kind of hierarchical structure there. And then this is a very good way to explore the machine learning finance paper series here. Okay, and the second part, they try to answer that is, and then they also find the US stock information can help to predict international market too. Okay, so this is another major finding in their paper too, to complement the hierarchical story. So what I talk about for the second point. Okay, I would highly recommend this paper to readers interested in international asset pricing and machine learning finance. Okay, let me go over the literature for this paper series. So first of all, it is related to return predictability. So we do see the GKX paper and other papers try to focus on machine learning methods to predict equity returns. And we also know a lot of paper to predict Chinese stock returns, okay, using machine learning methods. And we also see these methods can be applied to treasury bond, to corporate bond. So there's a long literature to apply machine learning methods to predict stock returns or other asset returns there. But the problem that is when we try to use these methods, then we want to see, do we really have the high dimensional predictors? Once you use stock return for the studies there, then we see for US market there are 2.4 million observations, okay? And then probably you only have like 1,100 or 1,100 features there. So we don't really have the high dimensional problem, 2.4 million compared to 100 or 1,000. Okay, so then do we really need the nonlinear methods to show the strength? Okay, different papers to show the nonlinear evidence in different market. And there's a lot of paper that is, they try to use the characteristic gap. Okay, so this is a lot of good point this paper try to use here, because for most papers in the equity characteristic predictability there, they try to standardize the characteristic cross-sectionally, like a uniform distribution. And then this paper, they try to explore a lot of parts. They simply standardize them also cross-sectionally to the zero mean distribution. And then they see the characteristic, the 95% and 5% gap there also help to predict equity returns internationally. And there's a lot of parts for machine learning literature that is trying to use machine learning to build different models, okay, to inference, like latent factor models there. And they try to use like text data or use picture data, try to predict stock returns or other equity or other asset returns there, okay. And the last paper I also try to mention related to international stock market, there is a lot of recent GFE paper. They try to apply high dimensional factor models to play with like time varying risk premium, time varying alpha, and time varying betas there. So there's a long literature to apply machine learning methods to study return prediction. And then I do find the advantage for this paper that is they find a different point to play with the hierarchical story. And I will show you some empirical highlights in a few slides. Okay, so the first table, first of all, they try to replicate the results for GKX. But the GKX paper, they use 900 predictors in their paper because they try to include interaction between characteristics and some other macro variables there. And then in this paper, they only focus on 36 characteristics. And then we see that the OLS results, actually, they're pretty well, okay? So first of all, do we really need machine learning methods there? OLS results, they're pretty well, and then they're, as we say, there are 2.4 million observations there. We don't really have the high dimensional problem. So the OLS result, they are quite close to the last of which numbers we see. But the authors find that, okay, using nonlinear methods, there's some improvement, okay, actually large improvement. So over the linear counterparts. So this is one thing they try to show on their main table. That is OLS does not fail. So we see pretty good numbers for OLS, but nonlinear models perform pretty well. Okay, so this is the table to replicate some results for the US data. And then they try to use the US model to explain something for the international market. Okay, so the second point that is, okay, the nonlinear model improvement. Okay, so when they use nonlinear model, they see for international market there, like, so 84%, they see the tree model outperform the linear model, or 97% the lower level model outperform the linear models there. So we do see large number of fraction that is the nonlinear methods outperform the linear methods. That used in the international market. So this is some solid evidence to show, okay, we do see some number in the international market. And the authors, they try to point out that out of sample R square can be sensitive to outliers. That's why they focus on the other two measures. Actually, for this part, I do have a small question about this too, because when we know that when you calculate the out of sample R square, the denominator, people usually use 0 as the benchmark because this is for individual asset. Okay, for outliers there, then usually if the outliers, that's the observed return, that happens to both the numerator and the denominator too. So that does not really affect out of sample R squared that much. But if the outlier is generated by the model, by the machine learning methods there, that might be a different story. So this might be a small question about this part. And they also try to show when to use nonlinear methods. The finding that is, okay, the performance of nonlinear models relative to linear models, that when the sample size is larger, then we see nonlinear models can have a better performance relative to linear models. Okay, so they show very good patterns for the different sample size in different international market, and then we do see a linear trend on that. Okay, and then a lot of finding for their paper, that equity prediction paper, they try to standardize their characteristic into a cross-sectional uniform distribution. So they will not see this part in their paper. But for this paper, they standardize the characteristics also cross-sectionally, but from a 0-1 distribution. So the gap between 95 and 5%, they will change over time. And then this paper confirmed with some previous studies that the US characteristic gap can be quite useful for return prediction internationally too. Okay, so this is a new finding. The previous paper, they find that this is useful for US market, and then they confirm that this is quite useful in international market too. Okay, so a lot of finding for this paper. So the last highlight I try to mention that is, okay, the Sharpe ratio improvement by incorporating more information. So in their paper, they have many tables in the paper. And then for the last field, they try to incorporate US information. And then they do find that adding US information help to predict or create a better performing strategy, okay, for international market, okay? Then I will come to my suggestion part, okay? So first of all, as the reader for this paper, there are many tables, first of all. And then I would have a very minor suggestion that is probably banned because different tables, you use different input variables there. And then it will be quite, it might be more clear to readers that we know which variables to use in the table. Okay, so just a very minor suggestion. Okay, but for but my other comments that is, okay, so as I said, when we see the prediction improvement for nonlinear models, okay, the level improve way more than linear counterparts there. Okay, but is there any way, so this might be a challenge question there because I don't see any other papers can show nonlinearity in their papers too. People usually show nonlinear model perform well than linear models, but how to like plot or visualize the nonlinearity, that part might be hard. And then this is the drawback for neural network too. And then because we don't know how to plot the nonlinearity there. And then the question might leave that whether the improvement might be from regularization from the data, or nonlinearity from the data there. Okay, and my last comment that is, okay, are similar characteristics or similar models, okay, in different markets that show international market integration. So are the characteristics play the role there, or the model play the role there for the market integration? Okay, because we see we can use the same US model to predict different international market. So which are the reason we can see the market integration? And then probably there's a more hierarchical structure worth investigating in this part too. Okay, I think I'm over time a little bit. So, so Darwin, do you want to respond to my question a little bit, or you want to answer question from the chat window too?
Yeah, thank you for your comments. Excellent. We will definitely think more about all these. The nonlinearity. We can plot something. In the earlier drafts, we do have some plots like showing, like for example, the size effect of China that people talk a lot about. And then we in fact have some nonlinear relationship. But we also think it's not just the nonlinear relationship; it's also the complex interactions among the predictors, like size interact with something. Those are more difficult to plot. But we will think through this. And also market integration. Yeah, we are also like thinking more about this. The fact that we can use the US return to predict international stock markets, that suggests some market integration, but again, not fully integrated. But again, because the local NNs do better. Okay, so now let me, I'll just like look at these questions online and then try to answer by Zhang Qi. Which sample period do we use for estimating OLS, which has no hyperparameters training? I think we use the same testing period, right? So like even when there is no hyperparameters for the OLS, but we need to check. Right? So we'll put that in the paper. Additional question is, how do we deal with missing values for the characteristics, which is common? Griffin has the answer. Drop it. Okay, so that's easy. So we just drop the missing value. But again, we require at least 100 stocks that have non-missing values for the 36 characteristics for 3 years. So because otherwise the market will be dropped. Okay, so but for individual stocks in that market, then when there are some missing values, we drop them. Any other comments?
So I have a question. Thanks for the great presentation. So your result, you observe the fact that as you have a less sample size, the performance of the tree over the linear regression model is getting worse and worse. and acknowledge the fact that actually that's a very intuitive, but you claim that's a problem of overfit. And my question is that how can you identify that's a problem of overfit but not underfit? Right. So intuitively, we know that the tree overfits the data because when you have a lot of data, it grows very, very deep. And to the extreme, it just have one data observation in each leaf node, and it fits noise and overfit the data, right? So the size of the tree is a great indicator of that. So actually I suspect that it is because the more data you have, the tree tend to be larger, and the less data you have, the tree tend to be smaller. And actually, the tree is essentially a step function. So as your tree becomes smaller and smaller, it's look more and more like a linear regression model. So I'm not sure what is the fact, but intuitively, I believe it is a problem of underfit, but rather overfit. And I think maybe you can check like the size of the tree to confirm this point.
Okay, that was a great suggestion. We will definitely check the size of the trees. In fact, in an earlier draft, we compare the in-sample R-squared and the out-of-sample R-squared. So we see a large drop. The in-sample R-squared are quite big. The out-of-sample R-squared like usually drops to negative value. And that's where we infer is overfitting. But in this version, we dropped that analysis because we try to say R-squared is not a good measure. So that's why we actually dropped this analysis from the paper. But that was what we did in the past. But we will definitely check the size of the trees again. Yeah, thank you. And I think there is an additional question here. Have we controlled for economic shocks, political factors, religious factors, institutional factors within different countries could relate to market integration? Yeah, these are great suggestions. We haven't. So right now we just use the stock characteristics. We don't really use anything. So the idea we have is we do something simple. We just follow what people do for the US. We just apply them straight to 31 international markets. And how do we define the markets? We let the model, we let the machine decide. Okay, so but yeah, we can fit in more variables. Yeah, we can also possibly relate our results to the previous literature. Previous literature do show that the integration can depend on these factors mentioned here: economic shocks, political factors, etc. So we can definitely check these. Thank you.